Okay, so we were talking in the last one about there are two lenses here. One we think of as kind of the same as have lenses in our glasses. In the Indiana Jones movie, he has a jewel on the end of a stick that concentrates the light. But we also have this opening. So let's talk about just a plain old opening operating as a lens. So in our Aristotle class, those of you who haven't taken it in Newton haven't heard about this, but in our Aristotle class, we just got finished with a unit where we followed in the footsteps of Aristarchus to calculate how far the moon is from the sun, or how far the sun is from us compared to the moon. And in order to do that, Aristarchus had to time the eclipse. And what he did was he compared the time it takes for the moon to cross entirely in front of the sun versus the time it takes for the moon to go once around the Earth, which would be a lunar cycle. And in doing that, he's able to figure out quite a lot about how far we are from the sun and how big things are. In order to time the eclipse, Aristarchus was able to fully do this, and some of you may have done this recently when we had the eclipse across most of the United States. So I know not all of you are in the United States, so it definitely wasn't visible to Costa Rica. I don't think it was visible to Orion in Alaska. I'm not sure. Oh, and the Cayman Islands now. So so definitely some of you weren't in the visible part for this eclipse. But the ancient Greeks were able to watch it. Just the openings in trees, we're used to thinking of those as just little spots of sunlight. What we don't realize is those openings, those round openings in trees are actually lenses showing us the image of the sun. And we can see that most clearly during an eclipse, where each little spot of light that would be coming between these leaves is actually a picture of the sun, and you can track the eclipse by looking at the pavement. So Aristarchus didn't have to look at the sun. Aristarchus didn't have to make a viewer using a box. He could have, but he was able to just look at the ground and watch the eclipse as it moved across the pavement. In knowing how to do this, one of the things, again, this gets back to the Greeks understanding light as being made up of particles that operate in straight lines. So one of the things that you're able to do if you understand this principle, which the Greeks did, is you are able to make a camera obscura. And we do have some ancient cameras that indicate that, yes, the ancient Greeks and others could make a camera obscura. And if you've never seen this, I really should go watch the video that I linked to on our class pages, because it's quite shocking to just watch the video, even if you're not going to make one. It's quite shocking that this works, and there's no electronics involved. There's no lens except for an open hole involved. So what you're able to do using the same principle here is in a dark room, close off a room, entirely darken it, and open like a dime-sized hole in a window. There's instructions in your homework packet for doing this at home, using aluminum foil to cover your windows. And when you do so, the light will come in straight lines. And what happens is, what we see is the light from the top comes through the hole in a straight ray, and it comes down to the bottom. And a straight ray can come off the bottom, and it goes through the hole, and it comes, so now it's flipped. The image is flipped. And we can see that all along, as we move from bottom to top, from top to bottom, the rays will all come in and they'll be ordered. So here, if this is coming through and it goes straight, if it acts like it's a straight thing and it goes straight through, you can see that it's ending up it started out just below the red and it ends up just above the red. So the entire image is flipped. And here is a picture from the camera obscura that the video is linked to on our webpage. And there is no electronic projector involved. This is just, what you're not seeing is there is a window entirely darkened out except for a small hole. And it's projecting the daylit scene outside onto the entire wall. And notice that it's flipped. Now, it flips inside our eye as well. Here's another thing that I don't have in my slide deck. Inside your eye, the image is actually flipped of the whole world upside down. So the back of your retina, the image is actually upside down, and your brain flips it. So your eye, acting as a camera, actually produces the image upside down with the lens of your eye squishing and expanding to focus the light differently. And it actually produces it upside down, and then your brain flips it so that you perceive things as right side up. Okay. Let me talk more about the lenses. I'll come back and talk about these. Oh, I know what I was going to talk about. Oh, refraction. Okay, so this lens, this was a lens as well. This was a lensing technique. And what it did was it was just a hole. There's no glass here. But if we use a material, in the hole, we can get even better performance with it using something called refraction. Now, refraction is the bending of light when it goes from one medium to another medium. We talk in our Einstein Adds a New Dimension class, we talk a lot about whether or not it's actually slowing down. There's a difference between something called its group speed and how photons of light actually interact. Its group speed does in fact slow down, but the group speed of light will slow down in different media. So going through air, it's almost the same speed as going through a vacuum, and then going through water, it's much slower. And ancient people have known about this since they have been spearfishing for fish from the surface, because if it gives you an optical illusion that the fish is up here when the fish is actually here. And so ancient people have been able to compensate for this refraction and have known about this refraction for a long time. In fact, there are cave drawings that indicate this refraction and how you have to predict the fish in a different place than you see the fish. You can see this light bending here's some glass. In glass, light is about 40% slower than it is in air, and it causes the angle to bend. You can make different, this is a lens like a cross-section of a lens we're used to thinking of. And this lens, because it has different thickness of the material that's going to slow the light down, the different thicknesses of the material that slows the light down allows it to bend at different angles. And as it does, it focuses it. This is what is meant by focus. It focuses it at one point. Now, the ancient Greeks knew about lenses of this size. And part of the way we know that ancient Greeks knew about lenses of this shape is that the word lens comes from the word lentil. And lentil is a very common food eaten in the Greco-Roman times, and we can trace the word lens being used in the same way for visible light refraction so that you could focus things. We can trace it all the way back to when it was first described as a lentil-shaped piece of glass. So a lentil-shaped piece of glass, this would be a cross-section through your lentil, is what made our first glass lenses. Okay, I have to stop the video now for our next part.